We're only going to get to levers. We have wheel and axle, and then pulleys, and then chains and sprockets and stuff. That's in another presentation. There are 6 simple machines. We're going to be dealing with all of them. You have levers. Levers are a simple machine. That's a transmission and the shifter. That's a lever. Wheel and axle. That if you're changing like any kind of wheel on a car, or like you turn on the hose with a wheel and axle. Pulleys. Hopefully you've seen that. There's a pulley lifting that plane. And then there's an incline plane, like ramps. Wedges. The wedge in this picture is not the firefighter, it's the axe. So any type of wedge, there's a wedge in the door right now. And screws. There's a jack. A screw jack. Alright, so with all of these simple machines, there is some kind of mechanical advantage. A mechanical advantage is something that allows you to do something while using a different force than it normally takes. So like if you want to lift something, you can use one of these simple machines to lift it, and it'll feel like you're using a different amount of force to lift some sort of object, as if you weren't lifting it with some machine. So like if you have a lever, or I wish I brought like a jack or something. If you have a lever and or like on a jack, how many people have used a jack before? Like okay. When you're like lifting or jacking up your car, you're not using that much force at all. There's a mechanical advantage with the jack. So the jack can actually lift the 2-ton vehicle or whatever it is, or ton vehicle, and you're just going up and down, and it's really easy. That's what a mechanical advantage is. It's the ratio between the magnitude of the resistance and the effort force. The effort force is the stuff that you're inputting, or whatever machine you're doing, whatever. It's the input force, and then the resistance usually is like a weight in the opposite direction. And it's also dealing with the ratio of the distance that you're like applying the force and the actual distance that the other object moves. So like when you use a jack, you're going up and down a lot, and there's a huge distance for what you're doing, and then it moves up just a tiny bit. These are like opposing. The easier it is, so the less force that you have to use, the smaller distance the actual object moves. So like if you have to use a lot of force, you might move the object a lot. If you have to use a little amount of force, and it's really easy to lift a heavy object, you're going to be lifting that object in very, very small increments. So we'll learn how to calculate mechanical advantage for different machines. If you have a higher mechanical advantage, it's most likely easier to do something. If you have a mechanical advantage that's closer to 0, that's less than 1, that means it's harder to do something. Whatever machine you have is making it more difficult. A mechanical advantage, it's a ratio. Usually we'll just write it as a decimal, so 4 to 1, that writing that mechanical advantage, you can just write 4. If it's some type of fraction, you'll just divide it and write it as a decimal. A mechanical advantage of 4 to 1 means you can lift something, say like you can lift a 4-pound object, but it would feel like you're lifting a 1-pound object. It's like 4 times as easy. Same idea with the distance. If it's 4 times as easy to lift this object, like the amount of distance that you're inputting is decreased by 4. So like here, to lift this box this high, it's easier to push it along this wedge than it is just to lift it straight up. It feels like you're not lifting all of the weight, but you have to push it a farther distance. So it's easier, but you have to go for a farther distance to do the same thing. So there's a trade-off. Does that make sense? Are there any questions so far? So like if it's easier, you probably have to do it for longer. to get the same result as if you were not using some simple machine. That's what it says. Work, we talked about work a lot. This is something that you might have seen in physics. Work is defined as force times the parallel distance. The distance that I'm talking about is the distance that whatever object is moving has to be parallel to the direction of the force. So if you are pushing this way and you have this distance, like if you're moving in the same direction or you're applying a force in the same direction as the distance that you're moving, then that's how you calculate work. You just multiply the two together. If you're doing stuff at an angle, it might seem like you're doing more work, but you would actually use like components of the force. We'll get to that later. How many people have talked about or seen this equation, work equals force times distance? Yeah. Did you have physics and you see it or not? A lot of the stuff that we do is from physics, but we might write it differently, just from like an engineering perspective. You just have to be flexible because lots of classes in college will be different and lots of companies will have you write things differently. They'll have their own ways of doing things. Okay. One is okay, so a mechanical advantage, if you have a mechanical advantage of 1, that means you're doing just as much work as if you didn't have this simple machine. So if you have a mechanical advantage greater than 1, then it feels like you're doing something easier. If you have a mechanical advantage that's lower than 1, it feels like you're doing something that's more difficult. I feel like it's easy to see why you'd want a mechanical advantage greater than 1. Why do you think you would want a mechanical advantage less than 1? That makes it harder to do something. Can anybody think of anything? What? For a short distance? Is that what you're saying? So if you want to move something a really, 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 really small distance, but like, I know you have human muscles, and if you push a little bit, it moves too far. You can have some kind of simple machine that makes it harder for you to move whatever object it is. So like you can have really, really small movements. That happens a lot with like screws. If you turn it a lot, it feels like it's difficult and you're moving a tiny, tiny distance. So you could have stuff that's more accurate. That's true. What else? Anybody think of anything else? No? We'll see. There's stuff all around. We talked about that. Mechanical advantage can never be less than or equal to 0. You'll see why just when you calculate it. It's just by the definition. So if you get a mechanical advantage that's negative, you're using the wrong numbers, or you don't understand what you did. And you can't get a mechanical advantage of 0. Ideal mechanical advantage, that's what we're going to be calculating a lot. That's just ignoring friction and assuming ideal conditions. This equation would be something that you would write down if you were writing stuff down. IMA is ideal mechanical advantage. D sub E, I'm just going to call it DE, is the distance traveled by the effort force, so whatever you're inputting, probably, and then the resistance distance is dr. So you would calculate mechanical advantage for some type of simple machine. So this is just a characteristic of a simple machine. Actual mechanical advantage is something that you have to measure. So you'd have to actually measure the force that you're inputting, the effort force, and you'd have to measure the force of the resistance. So if you have a weight, you'd have to know that weight, and you'd have to know how much force you're applying to actually get mechanical advantage that's actual. So actual mechanical advantage is using measured measurements. Ideal mechanical advantage is just using calculations of what you think it is anyway. You can calculate efficiency by comparing ideal mechanical advantage and actual mechanical advantage. You just take the fraction of the two. We'll see that in a little bit. We talked about that. The gym. Look at the gym. All of these machines make it more difficult for you to do something. So in addition to doing stuff that's more accurate, if you want to build yourself, use machines that have a mechanical advantage that's less than 1. That way, if you want to feel like you're lifting, 100 pounds, you don't actually have to use 100 pounds. So you can have some compact machine.
How much would that be like in the ratio?
I don't know.
Real close?
What?
I think it'd be closer. I think it'd be pretty close.
I don't know what you're asking. What are you asking?
Like, how much would it be in the ratio? 100 pounds.
For you to feel?
No, you just like, it would be easier on you.
You wouldn't actually have to have 100 pounds to make it feel like you're lifting 100 pounds.
So you're saying 100 pounds on the machine is 100 pounds like doing something?
It could be. Depends on what machine it is. Depends on what you're working on.
Let's say exact 100 pounds. What I'm talking about, how much would it be like lift? Like -1? Or
These are specific situations. I don't know.
Oh, okay.
When we get to calculating stuff, we can play with the numbers and see what happens. All right, this is what the main idea for today. The first simple machine that we're going to talk about is a lever, and there's 3 types of lever, 3 classes of levers, and they're all shown right here. The first one, the one in the top, is a first class lever. The way I remember what first class levers are is by thinking of a teeter-totter. The green arrow, you'll see in a little bit, but the green arrow would represent the force of your effort. The blue arrow would represent the force of the resistance. We call the little triangle, the pivot point, we call that the fulcrum. The second class lever is down in the left. That's a wheelbarrow, that's how I remember that, where the pivot point is all the way at one end, and the resistance is against the effort like upwards, the resistance is in the middle, downwards. You could actually flip it over, it doesn't have to be that way, but for me to remember what class 2 lever is, I think of wheelbarrows. For the first class lever, I think of like a teeter-totter or a seesaw. And then a class 3 lever is just this, but the effort and resistance are switched. So it's not like flipped over. The arrows are switched. The effort is in the middle, and the resistance is on the outside. Let's see if you understand that. People are typing in like clicking this stuff. It's kind of annoying. I feel like I'm not paying attention. So could you stop? Thanks. For this type of lever, you can have a mechanical advantage that's bigger than 1, or less than 1, or equal to 1. It just depends on where you put the fulcrum, the pivot point. Which do you think? I'm going to ask, it's going to be a difficult question, but we'll piece it out. Mechanical advantage greater than 1 makes it easier for stuff, right? Mechanical advantage less than 1 makes it harder for stuff. Which one do you think between class 2 and class 3 has a mechanical advantage greater than 1? Meaning it makes it easier. You think it's easier to use the class 3 lever? Yeah? I wish we could try this. Okay, so that door is we can consider it a lever, yeah? If we want to make it into a class 3 lever, the weight of the door and the resistance and the hinges, that'll be the blue arrow.